Welcome back, everyone. In previous lessons, we discussed why we use sampling when conducting social scientific research. In this lesson, we're going to look at some of the different methods we have for drawing samples that we can ultimately analyze and make generalizations about. Here are the questions for this lesson. First, what's the difference between a probability and a non-probability sample? Second, why are probability samples preferable to non-probability samples? And third, what are the different types of probability samples available? Before we look at those different types, though, we need to discuss some key terms related to sampling. As your reading pointed out for this week, statistical theory assumes that we know the probability that each element in the population has of being drawn into our sample. The whole idea that we can use samples to make inferences about a broader population is rooted in this statistical theory and all of its associated assumptions. Which gets us to the first term, which is the sampling frame. This is simply a list from which elements in the population are drawn into a sample. As you'll see, sometimes the sampling frame is the entire population itself. At other times, though, the list is carefully designed based on some sort of stratification or clustering technique. All this is to say that we need to be explicit and upfront about whether the sampling frame is the same as the population or if it's different. If it's different, we need to discuss our methodology for coming up with that list in the first place. The next term is what we call a probability sample. All this means is that each element in the population has some known probability of being drawn into our sample. And I've got the note here that known probability does not mean that each element has the same probability of being selected. It just means that if it's different, we know what it is. And these are different from what we call non-probability samples, which are the opposites. These are just samples in which each element in the population has some unknown probability of being selected into our sample. And our final key point here is that when we're using statistical tools to make inferences about broader populations based on samples, probability samples are generally preferred when it's possible that we can create one. All right, let's talk about some different varieties of probability sampling. The most basic type of a probability sample is what we call the simple random sample, sometimes referred to by the abbreviation SRS. What it means for this to be a simple random sample is just that all elements in the population have both a known and an equal probability of being selected into our sample. This means that if our population consists of 1,000 different elements, each element in the population has a 1 out of 1,000 chance of being selected. The other key point here is that when we're doing simple random sampling, the sample frame, that list from which elements in the population are drawn into the sample, this is the same as the entire population. It requires that we actually have a list of all possible elements in the population. And what I would encourage you to do here is recall back to the previous lessons in this module where we discussed some of the difficulties associated with conducting a census here in the US. But assuming that we have that list of every element in the entire population, the way that we start drawing those elements into our sample in the simplest example is just to place all of the elements into a hat, for instance, and then draw out the number of names until we reach the desired sample size. This is the classic example that your book gives, although technically this doesn't produce the same odds of each element being selected. The reason being that for each name you pull out of the hat, this lowers the pool and it changes the probability that each subsequent element is going to be pulled out. But nevertheless, even if that's the case, this still fits the criteria of being a probability sample because even if those probabilities change, we still know what they are. A better technique, though, is to take our list, our sampling frame, which in this case is the same as the entire population, and assign sequential numbers to each element on that list. So going back to our original example, if we have a population of 1,000 elements, we would number each element on the list 1 through 1,000. And then, if we wanted to sample, say, 100 elements randomly from that population of 1,000, we would use a random number generator to determine 100 random numbers, and then we would match those random numbers to our list. Those with the matching numbers get pulled into the sample. But as you might imagine, even though we call this a simple random sample, things aren't always so simple. And the most obvious issue is that getting a sampling frame that's the same as the population, getting that list, is often difficult or impossible. Also, the assumption with sample random sampling is that this technique is going to produce a representative sample of the broader population. But what I'd like you to do here is just a really quick thought exercise. I'd like you to pause and see if in your notes you can come up with some examples of why this might not always be the case. Why might simple random sampling not actually produce a representative sample? Well, now that you've had a couple minutes to think about this, we can take survey research as an example. Say that we want a representative sample that includes people with every relevant demographic characteristic that we might be interested in. That is to say, if we are sampling American citizens to survey, we are going to want the sample from everyone in the US to include men and women, people with all class and socioeconomic backgrounds, all religious, racial, and ethnic backgrounds. We'll want people who live in rural areas as well as urban areas. We'll want people with different partisan identifications and different political ideologies, so on and so forth. You get the point. But if a certain group makes up a very small percentage of the overall population, there's a very real chance that you'll exclude them when using simple random sampling unless you have a very large sample. The next technique, what we call stratified sampling, attempts to address that issue that we just talked about. The idea that simple random sampling might miss or exclude certain underrepresented groups in the population. The way these work are, they're still probability samples, but what we do is we take all of the elements in our population and we divide them into some sort of group, what we call strata. So say for instance, we want our sample to be representative of race based on whatever racial categories are included in the census. What we would do is we would take our list and we would divide everyone on the list into whatever relevant racial category there is. And then we would randomly select elements from each of these different strata until we get a sample where the proportions of each group in the sample match the proportions in the population. So here again, the sampling frame is still the entire population. It assumes that we have that list of all different elements. And it also assumes that we know what the population proportions are. Again, we usually get this from census data, but as we've discussed before, census data can have its own unique sets of issues. Nevertheless, this approach lowers the probability that certain small groups in the population will be excluded from our sample. And we say that this is still probability sampling because elements in the population may have different probabilities of being selected depending on which strata they're in. That is to say that if you're in a member of a small racial group in the population, you're going to have a higher probability of being selected into the sample than someone else. But even though these elements might have different probabilities depending on the strata, we still know what the probability is. All right, and then the final type of probability sampling we're going to discuss is what we call cluster sampling. As we just mentioned, both simple random sampling and stratified sampling techniques assume that we have a complete list of our population. That's our sampling frame. But what happens when no such list is available? I keep talking about public opinion polling here in the United States, where we do have a wealth of census data, even though there might be some issues associated with it. But if we're trying to do public opinion surveying in developing countries that don't have the resources to conduct high-quality censuses, we're not going to have that list available, and we're going to have to turn to some different techniques. And that's where cluster sampling comes in. This is a probability sample in which the sampling frame, as the name implies, initially consists of clusters. So what are clusters? Well, in public opinion polling, clusters are usually some sort of geographic block. So what you'll do is you will divide a geographic area, say a country, into different blocks. For instance, these might be subnational units, states, countries, neighborhoods, so on and so forth. And then from that, you're going to randomly select a subset of these blocks. This is what will be our sampling frame, because people that weren't in a selected block can't actually make it into the ultimate sample. From there, once you have the sampling frame of a set of randomly selected blocks, you'll randomly select elements from each of those blocks until you reach the desired sample size. And oftentimes, cluster sampling can be a multi-stage process. This is what we call multi-stage cluster sampling. Again, we can think of an example here in the US to see how this would work. Say we want to conduct a public opinion survey using cluster sampling. Well, the first thing we will do is we will select a subset of states. This is going to be our initial cluster. From there, we'll select a subset of counties in each of those states. From there, we'll select a subset of neighborhoods in each of the set of counties that we selected. And we'll keep doing this until we get down to the household level in each neighborhood. And again, this is still probability sampling because each stage in the cluster sampling is random and we know what the probability of being selected out of that cluster is. So those are all examples of probability sampling, and we said at the get-go that probability samples are preferred to non-probability samples. Nevertheless, non-probability samples are very common in social science research. Often, these are what we call convenient samples. And in terms of statistical assumptions, they're a little problematic because we don't know the probability that each element in the population has of being selected into our sample, and oftentimes we really don't even know what the sampling frame is or what it looks like. The classic example that you're going to look at in more detail in the next lesson is the opt-in online survey. We all know how common these are nowadays. And using these convenient samples, we can at least approximate representativeness using what we call sampling quotas. Your book discusses these in a little more detail. But even if we get what we think is a representative sample, it still violates some of these statistical assumptions because we still don't know whether the sample is different from the population along other dimensions because we're not using random selection techniques. This can create sampling bias, which is problematic for making causal inferences. But depending on what we're doing, a more or less representative sample, even if it's not a probability sample, can sometimes be acceptable. And one of the examples of when this might be okay is in conducting online survey experiments. We'll talk more about these later on in the semester, but this is an incredibly common tool in social science research right now. Largely relies on these opt-in online surveys. And the reason that it's not so problematic is that in experiments, we're interested in isolating treatment effects, not necessarily in making inferences about a relationship between two factors in a broader population. As you'll see through random treatment assignment, this holds all variables of interest, both observed and unobserved, constant, and we're able to isolate the effect of one individual treatment. In this case, non-probability samples can be acceptable in some instances. And then non-probability samples are also really useful for collecting pilot data. The idea here is that if we have a theoretical hunch about a relationship and we want to test it using a quality sample, we want to make sure that we're not wasting our time and resources going out and collecting this sample to look for a relationship that isn't really there. So we might look for evidence of a relationship in a cheap convenience online sample and then go and retest our hypothesis using that better quality data. Okay, to recap our main points from this lesson, we've said that samples come in one of two varieties, either probability or non-probability samples, and that the difference is whether or not we know the probability that an element in the population has of being included in our sample. We said that probability samples are generally preferred to non-probability samples, and the reason for this is that random selection reduces sampling bias. Finally, we said that simple random sampling requires that we can identify all elements in a population, and because this is often not feasible, we have to turn to other probability sampling methods, such as cluster sampling or stratified sampling.